Afternoon. So we're going to start our lecture, and I hope nobody is going to interrupt after this. You see, after I say that, somebody ask for admission into the classroom. Okay, so already 2:06. So as we have only 1 hour today, so I'm going to again continue with the tutorial discussion. So let's start. Okay, so I need to bring you back to question 2 because during last class, the Jingwei was so excited he detected something. All right, so let me go back to question 2 and make a correction. Yeah, so I actually made a mistake here in plotting the constellation diagram for 0, 1, and 1, 1. All right, so basically, if you refer to the equation, okay, if you refer to the equation, when we have a cosine omega t plus pi over 2, right? If you try to work it out, if you say when omega t is 0, then cosine will be cosine pi over 2. So the output st will be 0. All right, and then if omega t is pi over 2, then the whole bracket will be pi. So cosine of pi will give you minus a. All right, so it's the same as if we actually shift the axis, the y-axis, by pi over 2 over here, then give you a minus sign. All right, so this is a minus sign. Okay, so therefore for 0, 1, the point should be here. All right, minus a, which is the minus sign here. Okay, and then for 1, 1, 1, 1 here again, if you were to substitute the value for omega t, when it's 0, then this one in the bracket will be 3 pi over 2. So cosine of 3 pi over 2 will give you 0. But when this is pi, right, when omega t is pi, so you need to find the cosine of 2 pi, which is 1. Right? So this is actually equivalent to a sine wave. Right? It's like you shift the y-axis to here, 3 pi over 2. So that will give you a sine wave. So a sine wave, that means you need to put your, the symbol is actually located here for 1, 1. Okay, so Jiwi, no more confusion, yeah? Okay, so let's move on to, you want to correct that first in your record, then move on to the next question, tutorial, question 4, right? So basically, in short, if you see a plus pi over 2, a plus actually is in this direction. Negative is in this direction. Okay, so that is where I make a mistake. Okay, shall we continue with this tutorial and then question 4? I actually asked you to work out for polar signaling, right? So let's check your answer because I need to discuss for polar signaling. So for polar signaling, you should get your A must be greater than 4.8 millivolt. All right, so the minimum is 4.8 millivolt. And then power at the receiver need to be minus 49.4 dB. So that means your power at the transmitter need to be at minus 19 dB, 19.4 dB. And if you convert to watt, that will be 11.52 milliwatt at the transmitter. All right, and then at the receiver is 11.52 microwatt, right? Micro, this is micro, this is milli. And that is for half wave. And then for full wave, if you were to transmit using the same amplitude, then your power at the receiver will be about 23 microwatt. So power at the transmitter will be at 23 milliwatt. Okay, you get this? Okay, you should get this. Then let's do a comparison, right? We've done so much calculation for what? Basically, we want to compare their performance. Okay, So now we just want to compare the half wave because we actually have the graph for half wave in our lecture notes. So if I were to use on-off keying half wave, power is a square over 4. The power at the receiver is 23 microwatt. And then if I were to use polar half wave, where the power is a square over 4, a square over 2, then I need a power of 11.5 microwatt at the receiver. All right. In order for the probability of error to be, this one is for probability of error to be less than 10 to the power minus 6. All right. Okay, so the next thing I want to do today is to actually relate the power to energy per bit, which is EB, right? Because in your practical later on, you're going to see EB and not EV and not. Yeah. So what does EB and not mean? EB means energy per bit. All right, energy per bit. And therefore, to find energy per bit, we take the power multiply with the bit duration. Okay, power multiply with bit duration. And what is the bit duration? Oops. Let me bring it down. Okay, the bit duration here. We have a half wave rectangular pulses transmitted at the rate of 10 kilohertz. At the rate of 10 kilohertz. So this is half wave at the rate of 10 kilohertz. So that will give us the bit duration of 10 to the power of minus 4 seconds. All right. So 10 to the power of minus 4 seconds. And that means our bit rate is 10 kilobits per second. All right. Our bit rate is 10 kilobits per second, right? How do you get our bit rate? Bit rate is 1 over TB, right? 1 hour bit duration will give you your bit rate. And this corresponds to a bandwidth for the signal. The bandwidth is 10 kilohertz. All right, 10 kilohertz. So the minimum bandwidth is this, for this signal is actually 10 kilohertz. Yeah. So if you were to calculate again the EB will be power times TB. So you take 23 microwatt, and then you were to multiply with TB, which is 10 to the power of minus 4. All right, that will give you an EB of 2.3 times 10 to the power of minus 9 watt. Okay, these two quantity are in 10 to the power of minus 9. Yeah. And what about N naught? How do we calculate N naught? All right. So again, N naught, to get N naught, we take the noise RMS value. All right, the noise RMS value is 1 millivolt. So that means the noise power is the square of the RMS voltage, right? So the power of the noise is 10 to the power of minus 6 watt. I square this one, I get this one. All right. Then that give me a N naught. N naught actually is the power spectral density and is computed by taking the power of noise divided by the bandwidth. All right, power of the noise divided by bandwidth. So with the bandwidth of 10 kilohertz here, so our N naught will be 10 to the power of minus 10 watt per hertz. All right, N naught will be 10 to the power of minus 10 watt per hertz. All right, so now if I were to calculate EB over N naught, that means I take this one, I divide by N naught, right, 2.3 nanowatt divided by N naught, which is 0.1 nanowatt per hertz. So that will give me, convert to dB, that will give me this much. EB over N naught for OOK, half wave signaling, is 13.6 dB. All right, and then for polar, again, I take this value, divide by this value, and then take the log, because this is already in power, right? So I take 10 log of the ratio. They will give me in dB. For polar signaling is 10.6. Okay, and then if you were to compare this result with the graph that I show you during lecture, so to get the probability of error of 10 to the power of minus 6 or better, so your line, you should draw your line here. I'm not sure whether I can draw properly here or not, because my this one note somehow is not, the resolution is not that good. So let's say I want to Okay, 10 to the power minus 6. No, I can't. Okay, let's say somewhere here. Okay, I want it better than 10 to the power minus 6. So it should be below the 10 to the power minus 6 line. Yeah. I'm not able to move this line up because of the resolution in here. But in your discussion later on for your assignment, you need to draw your line here. You need to draw your line exactly at 10 to the power minus 6. And then you get the EB over N naught. Okay, so this one actually is EB over N naught as well. Okay, why EB or not? Because we actually take 20 log here. Okay, so you see that for polar signaling, all right, it's about, yeah, about 10.6. This is 11, right? This is 10, 10.5, somewhere there. And then this one, you also give you about 13.6. All right, if you draw the line a bit further up. So that actually jive with our calculation. Yeah. Then it also shows that the OOK, all right, to achieve the same probability of error, the on-off keying basically need to have extra 3 dB power. All right, extra 3 dB power as compared to your polar signaling. Okay, so in here we are actually comparing the probability of error curve for OOK and polar signaling, on-off keying and polar coding. All right. So in your discussion for your assignment, again, you plot your bit error rate graph and then you compare this way. Okay. So do you want to take this down?
Yes,
Okay.
please.
So let me arrange it nicely for you.
Vanis.
Okay, so let's discuss the next question, which is this one here. So in this question, we have an audio signal of bandwidth 4 kilohertz, sample at the rate of 25% above Nyquist rate, and quantize. Yeah? Quantization error is not to exceed 0.1% of the signal peak amplitude. Resulting quantized sample are now coded and transmitted by Fornery pulses. Yeah? So determine the minimum number of Fornery pulses required to encode each sample. Yeah, required to encode each sample. So to actually do this, we need to work out our n first. All right, we need to find out each sample got how many bits first. Yeah, because we want to know how many pulses we need to encode each sample. So that means we need to find our sample, how many n, how many bits are there in a sample. All right, and we can actually compute this by using this clue here. Yeah, this clue in the question. And if you want because to calculate bandwidth later, you need to calculate your sampling rate. So sampling rate information you get from here. Okay, 25% above the Nyquist rate. So, well, a good practice always just start whatever clue you have, you just write down first, and then you can straight away calculate your sampling rate, which is 10 kilohertz. All right. So that gives us that actually tells us that there will be 10 kilo samples per second. Yeah. And quantization error, 0.1% of the peak signal amplitude. So that means your L must be greater than 100 over 0.1. Yeah. And that suggests that your L must be greater than or equals to 1000. Yeah. So that will actually tell you your N must be greater than 9.96. Yeah. So to get the minimum bandwidth or the minimum number of ordinary pulses required, so we take the minimum value for N, which is 10. Yeah. And now how many pulses, how many ordinary pulses do we need to encode? 4 ordinary pulses do we need to encode this sample? This ordinary pulses means your M is equals to 4. All right, M is equals to 4. So for M is equal to 4, that means what is the N that you use for each pulse? How many bits is represented by each pulse? Your N will be log 2 of M, right? Yeah, this N is not the same as this N. All right, this N is the number of bits, right, encoded in each sample. This N is the number of bits that you can carry with one pulse. All right, now how many bits can you carry with one pulse? So now with in each sample we actually have 10 bits. All right, and then for if we use n-ary pulses, meaning m equals to 4, that means each pulse can actually carry 2 bits of information. Am I right? Each pulse can carry 2 bits of information. So we have 10 bits in each sample. So how many pulses do we need? Just simple maths only, right? As long as you know the concept, the maths actually is very simple. So for this question, I'm going to assume PSK first, yeah. So assume we actually use PSK modulation scheme. So with each Fornery pulse convey log 2, 4 or 2 bits of information, I will explain just now. So we basically need 5 pulses to carry one sample. All right, we need 5 pulses to carry one sample. Yeah. So now our sampling rate is 10 kilohertz. All right, so our pulse rate need to be 5 times now. All right, because the sampling rate is 10 kilohertz and we need 5 pulses to actually carry each sample. So our pulse rate need to be 5 times 10, which is 50 kilohertz. All right, which is 50 kilohertz. Therefore, our bandwidth now is 50 kilohertz. Okay. Okay, then let me explain further to help you to visualize it. So let's say now we have let's say 1011. Let's say we have then we have 5 bits 01 101100100122468 and let's say 10 again. Okay, so in four nary pulses, that means this 2 bit is carried by one pulse, this 2 bit is carried by one pulse, this 2 bit is carried by another pulse. So this is how you actually how the four nary pulses are used to carry the binary information. Okay. So this is one pulse. Okay, so this is another pulse. It don't care about how it means the what call that the phase. Let's say I just simply draw. Say this one is I use this pulse. Okay, this one maybe I use another pulse. Okay, so all these pulses, all right, we actually use one pulse, one oscillation to actually carry 2 bits. Yeah, one oscillation to carry 2 bits. Yeah, so therefore you see that for to represent to actually carry this entire sample of 10 bits, we actually need 5 pulses. Okay, maybe different phase angle, but we need 5 pulses. Okay, so that gives us that's how our pulse rate is actually multiplied by 5 of the sampling rate. Okay, so with the pulse rate at 50 kilohertz, that means our bandwidth is 50 kilohertz. Okay, is it clear for you? Don't take the other one first. The other side, we're going to leave it first. Don't want to confuse you. Okay, got question? Minus sign. Well, to be consistent, then to be consistent, you still take the plus sign and minus sign. Okay. Okay, then okay, do you want to take this down first? Let me scroll up a bit.
Anis.
Okay. So that is for A and B. And C, what is the bandwidth required if the data is transmitted by binary pulses? Okay, binary pulses, that actually binary pulses. So in this case, for binary pulses, that means if we are using two PSK, right? We're using two PSK. Um, okay, so for two PSK, then you need to compute. Where is two PSK? Okay, so as far as two PSK is concerned, that means each pulse is now going to convey 1 bit of information, right? All right, 2 PSK means m equals to 2. M equals to 2. So in this case, your C and D, I'm going to answer together. In 2 PSK, each pulse is going to convey log 2. Again, this is m is equals to 2. So each pulse convey 1 bit of information. All right, we actually done that previously when we sketched the waveform. So now with a bit rate, no, this is carrying 2 bit of information. So what do we need for our, let me see, so bandwidth required. Bandwidth required. So now 4K, we have 10K, 10,000 sample per second. All right, 10,000 sample per second. 10,000 sample, and each sample is wait, where am I? Okay, this one I'm for C actually this one this is the answer I actually did for the baseband, so I don't want to take that one. So I changed the question, but I forgot to change the answer. Okay, so if we are to using two PSK, right? So each pulse actually convey 1 bit of information. All right, each pulse actually convey 1 bit of information. Now, with the bit rate of 10K bits per second, how do I get this bit rate? How do I get this bit rate? This RB, basically, I take n times fs, right? Where my n is 10, my sampling rate is 10K. So that will give me 100 kilobits per second. Yeah. So, so with the bit rate of 100 kilobits per second, and I need one pulse to convey 1 bit. So that means my pulse rate is 100 kilohertz, because I need one pulse for 1 bit. Yeah. Therefore, our bandwidth is 100 kilohertz for 2 PSK. Yeah. And then for 8 PSK, then each pulse is actually conveying 3 bit of information. All right, each pulse is conveying 3 bit of information. So now again with the same number of bits per second, then our pulse rate will be 33.33 kilohertz, and then the bandwidth will be again same as the pulse rate, which is 33.33 kilohertz. Okay.
But Miss,
Okay. So again, this is a theoretical calculation. And if you were to, let's say, look at this sample again, let's say I have a sample. Let me change color. Let's say my sample data. Again, is let's say 11010011010. Let's say this is my 10 bit. All right, 10 bit data. 2, 4, 6, 8, 10. My 10 bit data. All right. So to actually carry this 10 bit data, all right, so you can actually perform BPSK. All right, BPSK, that means you use 1 pulse to carry single bit. So your 1 will be carried by, let's say, this one, and your 0 will be carried by negative, right? This is how you actually carry your 1 and 0. And if you were to use QPSK, all right, so if you were to use BPSK, then you need how many pulses? You need 10 pulses, right? 10 pulses to actually carry each data, each sample. And then if you use QPSK, you need 5 pulses to carry your data, this 10-bit data. But if you try to use 8PSK, if you try to use 8PSK, that means 8PSK you are going to represent 3 bit with 1 pulse, right? You will try to represent 3 bit with 1 pulse, and in this set of data, you only have 10 bit in each data, in each sample. So therefore, you will have a problem later on. This 1 bit, how to sample, how to carry this 1 bit. Yeah. So normally, for this kind of data, you can't really use APSK. You can, because you can't really break your sample evenly into 3 bit. Yeah, you have 1 excess bit at the end. Okay, same thing. You can't also use 16 PSK, because 16 PSK means we're going to use 4 bit, right? 4, then you have 2 bit here excess. How to carry this 2 bit? All right. So again, actually depend on how your data look like, how many bits you have in each data. Then only you can think about what kind of what M level can you use for your PSK. So same thing for FSK also will stay the same. All right. So again, it depends on the size of your data. Okay, so this is just for theoretical calculation, right? In practice, you may have problem here. So let's I analyze, or we summarize our findings from above. So if you look at the table, you apply the formula. All right. So I'm going to apply this formula that is given in the lecture notes. The bandwidth for MPSK is actually 1 plus R times RB over log 2M. All right. So now with my data rate, RB equals to 100 kilobits per second. Now, if I were to use sync pulse to perform the modulation, so and then if for baseband, if I were to send the pulses as it is, all right, then that means I don't do modulation. Then the minimum bandwidth I need to transmit the binary signal as it is 50 kilohertz. That's the minimum bandwidth. Then if I were to use 2PSK modulation scheme, all right, I will need twice the bandwidth, all right, because this is um, logical, isn't it? Because this one no modulation, this one is modulation, yeah. And 2PSK modulation is like you multiply the baseband signal with the carrier, right? You multiply with the carrier. So the moment you multiply with the carrier, you actually double the bandwidth requirement already, just like our double sideband suppressed carrier signal. Okay, and then if you were to use the 4PSK, so in 4PSK, your log 2 4 log 2 of 4 is 2, right? So therefore, your bandwidth requirement becomes 50 kilohertz. Yeah. Then for 8 PSK, your bandwidth requirements reduce further because this will be divided by 3. Yeah, and then for 16 PSK, this will be divided by 4, and that gives you 25 kilohertz. Yeah. So you can see, as far as the bandwidth requirement is concerned, when you increase your M, right? When you increase your M, then the bandwidth requirement reduce. All right. When you increase your M, your bandwidth requirement reduce. And with the bandwidth reduction in bandwidth requirement, that means your efficiency, your bandwidth efficiency actually increase. All right, your bandwidth efficiency actually increase. But again, if you were to compare with the probability of error curve for these few M levels for PSK, you see that in order to maintain the same probability of error, you have to increase the power as you increase your M. Right? We discussed this during lecture, so you might want to refer back again. And that actually reduce the power efficiency. Yeah. So when you use for MPSK, you can actually save the bandwidth by using higher M level. But if you were to do this, you may have to boost your signal power in order to maintain the same probability of error. Yeah. And if you were to modulate the carrier using raised cosine pulses where R is equal to 1, all right, and then the raised cosine pulses actually will require twice the bandwidth of the original bandwidth of sync pulses that you use sync pulses. So therefore, when you perform the modulation, the 2 PSK now require 200 kilohertz, okay, instead of 100 kilohertz. Yeah. And then for 4 PSK, again double. But as you can see, the same trend actually follow. As you increase your M, you need less bandwidth. Yeah. Okay, so that is for MPSK. And if you were to compare, let's say, because they say 4 Neri pulses, now the question say 4 Neri pulses, it never say it's a PSK or FSK, right? So I'm going to compare again the same data with for FSK. So FSK, the bandwidth requirement actually depend a lot on how the signal is being detected at the receiver. Do we use non-coherent or do we use coherent? Yeah, PSK only coherent is used. You cannot use non-coherent detection method for PSK. All right. For FSK, you can have a choice between the non-coherent as well as the coherent, and then the bandwidth requirement are different. All right. So for non-coherent, the equation for bandwidth is given by this expression, and the equation for bandwidth for coherent is given by this, right? So if you were to put the numbers in, okay, you will see that as far as in this case, I just want to compare R equals to 1, right? If R equals to 1, then my 2 FSK signal, if I will transmit the binary data using 2 FSK technique, I'll need a bandwidth of 400 kilohertz. Okay, compared to baseband, I transmit it as it is with raised cosine pulse. R equals to 1, meaning I transmit with raised cosine pulses. I need 100 kilohertz baseband. But once I modulate, I need 400 kilohertz. Okay, this is for 2 PSK. For FSK, this is for 2 FSK, sorry. For FSK, using the same equation, it suggests that you also need 400 kilohertz. Okay, so I guess this is they play with the frequency separation. Okay, you need to play with the frequency separation in order to get the same bandwidth. And then if you move on to 8 FSK, then you'll be 533 kilohertz. But the overall trend is when you increase your M level, you are going to increase the bandwidth requirement for FSK. All right, so this is the trend is different for FSK. Okay, so for MFSK, when we increase our M, we actually increase our bandwidth, and therefore it reduces our bandwidth efficiency. Yeah, and that is for non-coherent. For coherent, the same trend. Yeah, for coherent detection, the bandwidth requirement is actually lower as compared to non-coherent. All right, for non-coherent, because you use the you're going to use filter, right, to actually recover the signal that you want. So when you use filter, then definitely you need a wider bandwidth to allocate for your filter design. But when you use coherent, you're going to use a carrier, right? So you use a carrier, then the frequency separation can be narrower. So therefore, you see that for coherent detection, the bandwidth requirement is lower, right, as compared to non-coherent detection for FSK. But there's still the same trend as you increase somehow this number is a bit weird. So if you I take this from I take this equation from a book. All right, so when you move to FSK, somehow the bandwidth actually drop. Yeah, it should increase. Why it drop? Okay, so but then if you compare from 4 to 8 to 16, from 4 to 8 to 16, when you increase your M level, the bandwidth requirement increases as well. Okay, but for FSK, we also seen that in lecture, when you actually increase the M level to M level, that give you bigger bandwidth, but at the same time, you are going to have a drop in the probability of error. Right? You're going to give you an improvement in the probability of error. So again, with the increased M level, basically it's going to increase your energy efficiency. Okay, so you can refer this to lecture notes. Basically, I think lecture notes explain in more details. So what else can I say about here? So this is, I think, yeah, okay. So then we are, okay. Any question on this before I move on to next question where we calculate the signal amplitude? Question 6. Bandwidth equals to RB over N. Yes, for PSK, MPSK. MPSK. Yeah. And this log 2M basically is N. Okay, I use M here because when we talk about n-ary PSK, we actually put 2, 4, 8, 16. But again, you don't confuse yourself. A lot of students, they confuse. This N, what is this N, what is this M, you know. So you don't confuse yourself. For this 2 PSK, your N is 1. All right, so this one, your N is 2. This one, your N is 3. This one, your N is 4. All right, and this is actually log 2, M is actually N. Okay, this equation, I leave it as log 2M because I want to take this number. Okay, and baseline frequency is a frequency without carrier. Baseband is no carrier. Baseband signal means no carrier. All right. Okay, so then let's discuss the next question then. Next question actually is some simple calculation about, okay, I bring in the N naught into the discussion. So now find the signal amplitude as assume rectangular pulses for polar baseband signaling that give probability of error 10 to the power of minus 6 in a channel with N naught equals to 10 to the power of minus 7 watt per hertz with a data rate of 1 kilobits per second and 100 kilobits per second. Okay, so this is only for polar baseband. All right. So for polar baseband, again, the probability of error is equals to the Q function of A over sigma. All right, A over sigma, that is need to be 10 to the power of minus 6. All right, so that gives us A must be, A over sigma must be at least or equals to 4.75. Is it 4.75? 4.8 or 4.75? Let's check our this one. I did this some time ago, so let me confirm. Oops. My appendix. Okay, appendix. Yeah, okay, 4.75 because okay, because I want 10 to the power of minus 6. So I take 4.75. So let me share my screen now. Okay, again, if you refer to the Q function table, so 10 to the power minus 6, so I take this one, and this is about 1 times 10 to the power minus 6, so that's why I take 4.75 here. All right, so that will be Q A over sigma is 4.75. So that means my A must be 4.75 sigma. All right, so how do I relate sigma to N naught? All right, we can relate sigma to N naught by using this equation. All right, sigma equals to root of N naught over 2 TB. All right, root of N naught over 2 TB. And TB basically is 1 over RB. TB is your bit duration. All right, TB is your bit duration. So 1 over TB basically is your RB. Okay, so therefore your sigma is N naught RB over 2 because we know our bit rate. Okay, our bit rate is 1 kilobits per second. So that put your numbers in 1 kilobits per second. So that will give you your A must be 0.0336 volt. Okay, that's your signal amplitude. So that is what, 33.6 millivolts. All right, 33.6 millivolt. Then if the bit rate is 100 kilobits per second, 100 kilobits per second. So now you put your bit rate as 100 kilobits, that is 10 to the power of 5, right? And divide by 2, take the root of it, multiply with 4.75. That will give you your amplitude must be 0.336 volt. Yeah, okay. This is 10 to the power of 2, so times 10. Yeah, okay. So that is, you see the amplitude is now 0.336 volt. So what can you say about this? What can you say about this? So when I increase my bit rate, okay, when I increase my bit rate, so in order to maintain the same probability of error, I need to increase my signal amplitude. Makes sense, isn't it? All right. So when our bit rate increases, we actually need to increase the signal amplitude in order to maintain the probability of error. Okay, so you may want to take this down. So this is for polar baseband signaling. Same thing, we can apply the same principle for BPSK. All right, for PSK, FSK, and so on, we can apply the same concept, yeah.
Miss, can you able to zoom out a bit?
Zoom,
Yeah, zoom out.
zoom out. Out, you mean smaller?
Yes.
But you got everything here already, what?
Okay. Okay, sure.
A is here, B is here. My handwriting sometimes is a bit what now, so I write too fast, that's a problem. Increase. I rewrite.
Done, Miss?
Okay. So I think that is the last question in our tutorial, right?
Yeah.
Okay, well, right time, 3 o'clock. So let's end the class here because I have another class supposed to start now. Okay. Bye bye then. For those who are not going to attend the practical session, you may leave.
Bye, Miss. Thank you, Miss.
Bye bye.